let's talk about the graphing trig functions. All right, I've typed in y equals cosine x. Now, we have the circle, the unit circle, and as you go around the unit circle, imagine that circle there, the x value will go from positive to -1 to +1 to -1. Well, that's what we're trying to graph here. That starts at +1, and as we go around the circle, it goes down to 0 at pi over 2. Pi is 3.14 divided by 2. That's about 1.57. So by the time we get to 1.57 radians, we're at 0. That's at the top of the unit circle. And then if we keep going around the circle, we get to 180 degrees, or pi, and the cosine there is clear to the negative side, -1, and then we go further to the bottom of the circle and to the top of the circle. And so the x value goes from 1 to 0 to -1 to 0 to 1. And 1 is at 2 pi once around the circle. Now, that's just the y equals. Now I'm going to turn that one off. And now I'm going to look at the red one, and it's got things that we're going to do to it. We're going to play with a, and a is right now 1. And a is called the amplitude. Now, if you take any function and multiply it by something, it causes a vertical stretch. So if I multiply it by more than 1, the height gets higher. If I multiply it by 2, as you can see here, now it goes from 2 to -2. And back to 2. And if I multiply by 3, goes from 3 to -3 to 3. So that's called the amplitude. One of the reasons you've heard of the word amplifier, it basically takes your sound waves and makes them louder, or increases the amplitude of them. There's a d. And the d at the end is outside also. This cosine, this stuff's inside. We'll talk about in a sec. But the outside stuff, this stretches it vertically, and this moves it vertically. So right now it's not moved up or down, but if I move it up or down, we get those places. So I'm going to move it back to where it originally was. So that's what d does. And they work just like you think they would do. If you put 2 in, it gets twice as tall. Oop, not B. If you put 2 in for A, it gets 2 times as tall, so double the stretch. Oop, B, it's got to be 1. 2, if you go to 3, it's 3 times as 6, it's 6 times as tall. 7, 8, 9, 10, it's 10 times as tall. What if you go to negative numbers? Watch how it flips when we go to negative. Okay? So that's what the amplitude does. It flips it or stretches it vertically. The d just moves it up or down. So I'm going to go back to 0. Right there. What's the c do? The c is subtracted from the x. So that's going to move it. Since I made it as a subtract, it moves it. If I go to -1, x subtract 1, it moved it 1 to the plus side. If I subtract 2, it goes 2 to the plus side. So just like we did transformations of other functions, that this controls where it is horizontally. So now I'm going to go back to 0 on that. And what's the b do? Well, b is times it. And if b says multiply it by 2, you would think it would stretch it out, make it twice as wide. But again, this is inside, so it does half as wide. So if I go to 2, you get twice as many curves, but they're each half as long. From here to here is now pi. You can see that's pi. And if you click there, this tells you it's pi 1. Normally, if the b is 1, the top is at 2 pi. And the bottom is at pi. But if b goes to 2, come on, move to 2, it shrinks each one. So it makes the period double, or the frequency double. So we get 2 waves by 2 pi instead of just 1. So that's another way to think about it. And if it was, now watch what happens if we go from positive 2, come on, move, to 1. Now if we go closer and closer to 0, it makes them longer and longer and longer. Then if I start going to minus, you can't really tell, but it's flipped it. The positive side goes to the negative, and the negative goes to positive. But since cosine is even, you don't notice any different. So now I'm going to move this back. Oh, stop that. Go back to what it was. Oops. Oh, it's stepping through. I don't want it to step. Stop. I want to put it back on. B equal 1. Okay. So now notice where the top is. Cosine is 1 at 0 degrees. And that's because on the unit circle, let's just type in a unit circle here. X squared plus y squared equals 1. So there's the unit circle. When we're at 0 degrees, the x value is 1. As we go to 1, or to pi over 2, the value of the cosine is 0. So you can see if I laid this circumference out here, it gets to here, and the cosine value is now 0 here. If I go to here, the cosine value is -1, and so that's what it's saying here. Think of this circle's circumference laying right here. So that length stretched out straight goes to here, and the cosine value, which is the x-coordinate, went from 1 to 0, and then went from 1 down to 0. And now if I keep going around the circle, the cosine continues to go negative and goes clear to -1. Then if I keep going around the circle, the cosine comes back, the x-coordinate comes back to 0. And if I keep going around the circle, the x-coordinate goes back to 1. Goes back to 0, back to 1. So that's keeping track of the x-coordinate. And the x-coordinate at 0 degrees, we put it on the x-axis, 0 degrees or 0 radians is 1. So that's where the cosine starts. Now the sine was the y-coordinate. Now the y-coordinate at 0 is 0. And it's 1 at pi over 2. So the sine will go from here up to there. So I'm going to type in y equals sine x. And that blue curve, you can see, goes from 0 to 1 because the y-coordinate for here is 0. The y-coordinate for here is 1. Then it goes back to 0 for the y-coordinate. Then it goes to -1. And then it goes to +1. So the sine is just the cosine curve shifted over. In fact, I can take the cosine and shove it sideways, pi over 2, to move it sideways. That's the c. So if I make it pi over 2, which is a little over 1, they will line up. It's about 1.6 or so. You can see how they line up, but let's move it back to where it was. Okay? So now, everything that worked like it did for the cosine curve does the same for the sine curve. So if I turn off the blue one and make this red one be the sine curve, now you can see that I haven't moved up or down. The c is 1 sideways, so let's move it back to 0. There's the sine curve. The y-coordinate here is 0, goes to 1, goes to 0, goes to -1, goes to back to 1, or 0. Goes from 0 to 1 to 0, minus 1 to 0 at 2 pi, 6.28. Okay, and you could play with these parameters and see how they adjust the sine curve just like the cosecant curve gets adjusted. So that's graphing sine and cosine. What about tangent? Well, tangent is sine over cosine. So anytime the cosine, let's graph the cosine here also. So there's the cosine, the green curve. And anytime the cosine is 0, since tangent is sine divided by cosine, this is going to be sine 1, the y value, 1, divided by the cosine value, which is 0. So so 1 divided by 0 would be undefined. So there won't be any tangent there. So if I graph the tangent, so this will be, let's see what color that is. Purple. There's the tangent curves. Anytime the cosine is 0 on the green curve here, you notice the tangent disappears. Again, the cosine is 0 at this place. The curve goes off. It avoids it. There's a vertical asymptote at, let's see, this is pi over 2. There's vertical line right there that can't equal. Let's draw it. Y equals pi divided by 2. And did it draw it? It's in black. Oop, that's y equals. I want x equals. Oop. X equal vertical line. There's the vertical tangent. Okay? Now, if you stretch or shrink them, that'll cause some things. So now let's turn, that's the tangent curve. I'm going to turn off my unit circle. I'm going to turn off the cosine. I'm going to leave these A, B, and C and going to go to tangent. Just see what happens to the tangent as we change the parameters here. So once again, A will stretch or shrink vertically. So if I go bigger, you can see how it's stretching. I left the tangent, the purple, on so you can see how it changes. And then if we shrink it by going to smaller values, 0 there. And if you go to minus, it flips them over. You can see how they're flipped over. There's a minus 0.1, minus 0.2, 3, 4, minus 1, minus 2, minus 3, minus 4, stretching it vertically. And this is going back to there. So I'm going to take it back to 1. Oop, almost there. There's 1. Now, what does the D do? Well, we know what that does. It moves it up or down. Okay? So it's back to not moved up or down. D is 0. C moves it left or right. Okay? And B increases how many there are, increases the frequency of them. So watch as I make this go more. It kind of looks like it's stretching them, but it's squeezing it horizontally. 2 times, if I go to 2, there's twice as many as there was before. You can see the purple one here, and there's the red one. And by the time this purple one finishes, we've got 2 of them, and then there's 2 red ones. From the red one would go from here to there. You can see that there's basically 2 red curves for each one purple curve. And if we went to 3, there would be 3 times as many, 4 times as many, 5 times as many. So it horizontally moves them. It compresses or stretches. So let's go back to 1. And it matches up with the purple. Now, that's tangent. If we go to cotangent, cotangent is cosine over sine. So I'm going to put the sine curve back on. The sine is 0 here. And tangent was sine over cosine. So sine being 0 in the numerator, that's why the tangent curve is 0. But if the sine is 0 and cotangent is cosine over sine, anytime the sine is 0, the cotangent is undefined. It'll have a vertical asymptote like the tangent had here. So let's turn that vertical tangent off. And I'm going to actually turn it back on at pi. Now you notice that the sine is 0 at pi, and since cotangent is cosine over sine, and sine is 0, there should be an asymptote here for the cotangent. So let's draw the cotangent. And now this is getting pretty messy, so let's turn off the tangent curve. You see when the sine is 0, there's an asymptote. The sine is 0, there'd be an asymptote. Sine is 0, there'd be an asymptote. Okay? That's because cotangent is cosine over sine. If the denominator is 0, we have an asymptote. You also notice that let's get the sine out of there. And if we look at the tangent curve and the cotangent curve, they look very similar, except that they're shifted because of where the cosine is 0 versus when the sine is 0, and it's flipped over looking. Okay? You may want to do all this on Desmos to get used to it. So now, the same thing happens if I put cotangent here. They now match up, and you could then stop that. Go back to regular. If we go to the sliders, the A will vertically stretch or shrink. So here's A stretching or shrinking and flipping over. So you could make them almost like the tangent if you pick the right numbers to change. But here's back to 1, the normal tangent curve. If you mess with D, it moves it up or down. You mess with C, it moves it left or right. And if you mess with B, you increase the number or decrease the number. You increase the frequency, how often they happen, or decrease the frequency. Okay? There we go. Okay. So what does sine's reciprocal is cosecant. So I'm going to turn this one off and change the purple to cosecant. The reciprocal of sine. Well, whoa, what's this? Well, let's turn on the sine curve and see what we have. You notice that it looks like it bounces off the tops of the peaks and bounces off the troughs. It comes down and shoop. Let's try to understand that. So cosecant is the reciprocal of sine, so it's 1 over the sine. Well, if sine is 0, 1 over 0 is undefined. Notice the sine is 0, there's an asymptote. Notice the sine is 0 at pi, there's an asymptote. At 2 pi over 3, 2 pi, there's an asymptote. Okay? Now, what if we did played with that. So now let's take a look at, I'm going to make sine be a sine of parenthesis capital B parenthesis x minus capital C close parenthesis plus D. So there's the sine curve with the same A, B, and C, A, B, C, and D as this one if I do cosecant here, CSC. Got the same A, B, C's, and D's. So watch what happens to the cosecant, the purple curve. Is that right? Yes. Well, I want to do it. I want you to look at the sine curve, the green one, and the red one. Okay? Now the purple is the normal cosecant, so I'm going to turn it off. So we're comparing the cosecant to the sine curve. And I always tell the students if they ever have to graph a cosecant, draw the sine curve first. And I hope you see why here. So what happens if I increase the amplitude? Well, here's the amplitude. If I increase the sine amplitude, look what happens to the cosecant. We're doing vertical stretch, but it also gets further and further. The low spot here and the high spot on these are still at the trough or the crest of the sine curve. And if I go smaller, notice how they get blunter, and then all of a sudden if I go negative, they flip over and go the other way. They stay on the crests and troughs of the sine curve. So if you can draw a sine curve, you can draw the cosecant curve. If you move it up or down, you just have to take into account that. So let's move it back so it's not up or down any. 0. And if you can move it left or right, just like the other one. They move the same way. And the B increases the number of them or decreases the number of them. Okay? And if you go to negative numbers, it flips them over, so the other side. That's because sine is an odd function, so something over here, if you flip it to the other side, you can see the difference. Right now, we've got it negative, so let's go to positive. Watch in the middle how it flips. See how it came back the other way? So the sine's going this way. If you go to the negative, it'll go this way. It flips it over the y-axis. This side goes to this side, and this side goes to that side. Same things work for the cosine, so I'm just going to change this to cosine. And I'm going to change this to cosine's reciprocal, which is secant. And you can see how you got the same looking graph. It's just now the peak is here as opposed to here. And now if you flip it over the y-axis, it looks the same. And that's because cosine doesn't care whether you're doing positive angles or negative angles, positive or negative. They look the same. Okay? Go back to 1. And as I said before, tangent and cotangent are reciprocals. And that's how they look together. And you can still play with the same sliders here to move things around. You can see that the tangent is an odd function, and so is the cotangent. So this, if we move b to the negatives, they will flip and go the opposite direction. See how here the tangent goes down this way, and the cotangent's going up. And then if I move B to the positive side, come on, move. They flip side. They flip over the y-axis. That's the quick summary of graphing trig functions.